Centripetal acceleration. Does that show up? Yeah, I guess it does. It does kind of show up. Okay. See, I am winging this rubber stopper around my head. And there is great danger involved because I do not have goggles on. So I'm just going to let it drift. And so let's pretend this has constant velocity, or sorry, constant speed, because the velocity is continuously changing. Here's my question. Is there a force being applied to this rubber stopper? Pause the video here. If I said pause the video with an English accent, would you do it? Pause the video here and satisfy for yourself if there's acceleration. Is there a force on this rubber stopper? Anybody? Anybody? Yes, there is. The only thing that's applying the force to the rubber stopper, of course, is this string. And so one of the main concepts that you work on when you're dealing with centripetal acceleration is the fact that the acceleration of the rubber stopper is actually always directed right towards the center of the circle. So even though this rubber stopper is going around in circles, it's always accelerating right towards the center of the circle. And there are these geometric arguments about it, but this is the most convincing one I can come up with. See this string? It's the only thing that's keeping it going around and around. It's providing the force. It's always directed toward the center of the circle. The direction of acceleration is the same as the direction of the force, so it's always accelerating towards the center of the circle. So there's this awkward set of geometric arguments that get made, but I just think it's easier to say, yeah, there's only one thing keeping this moving in a circle. It's the string, and the force is directed towards the center. So anyways, there's the first thing about centripetal or uniform circular motion and the centripetal acceleration, always directed towards the center of the circle. And tomorrow we're going to find that the mass, or sorry, the force is also directed towards the center of the circle. Here's the other thing that everybody gets confused about. This is the other misconception. It's like when I release this rubber stopper, so if I'm trying to kill a dinosaur, or I don't know, I guess kill a dinosaur is a bit dramatic. If there was a dinosaur, I shouldn't kill it. It's probably pretty rare. Anyways, if I was to release it here, everybody thinks, oh yeah, if you release it right here, it's going to fly out this direction toward the camera in this case. But actually, in order for it to release in the direction I'm looking, I need to release it here. Okay, so the velocity is tangential to the circle. And so if I release the rubber stopper here, it's actually going to go that way. If I release it here, provided it's moving this way, it's going to go straight ahead. Okay, so that's the other misconception that commonly focuses around circular motion. Velocity is always perpendicular to the circle. Now, back in the old days, back in simpler times, we would maybe do what I always liked as a great experiment, which was seeing what the centripetal force was proportional to. So if I increase the radius, what happens to the centripetal force? Or sorry, and in this case, we're going to talk about the centripetal acceleration. Well, the centripetal acceleration would go down. Griffin, can you go get me a piece of white chalk?
Are you still recording?
Yeah, you're live on YouTube right now, getting a piece of white chalk. There's a big, oh, there's some white chalk right there. You can see it. Perfect. There we go. Okay. Anyways, centripetal acceleration. It's actually inversely proportional to the radius. So if I double the radius, I'll actually reduce the acceleration by half. And so it is inversely proportional to r, which is the radius of the circle. If I double the velocity as it wings around, I'm actually going to increase the acceleration by 4. And similarly, if we were just doing force, we would be increasing force by a factor of 4 just by doubling the velocity. And so it is proportional to v squared So back in a simpler day, I think back when we had like grade 13, you would do this as a proportionality experiment. And it's actually quite nice because there's like a lot of proportionalities involved. Okay, anyways, that's it. That's the centripetal acceleration equation right there. Because it's circular, the velocity at any instant, it could be described as a vector, but because it's always changing, we're going to simplify this a little bit. And we are going to try and express this in terms of period and frequency. And so we're going to change it up so that if we're not given the velocity, if we're given the period with which it goes around, or we're given the frequency with which it goes around, we can calculate the acceleration. Okay. So velocity, in this case, not the vector quantity, is equal to how far it goes around to go around the circle, which is 2 pi r, which is the formula for the circumference of the circle. In other words, there's the distance around the circle, and that's going to be divided by the amount of time that's required to go around the circle. And the amount of time required to go around the circle is also known as the period of the circle, and we represent that with a tau. Okay, so here's our new expression for velocity, but it's given in terms of period. Okay, so instead of v squared, let's push in this really terrible looking thing over here, the 2 and the pi and all that sort of stuff. So instead of v squared, I'm going to put 2 pi r over tau, and that's all divided by r, the radius. I have to be careful or my r's are going to turn into stylized v's. And it's the velocity squared, so we'll square that. Let's get ready. Let's do some of that fraction stuff. Okay, so in other words, this is equal to 4 pi squared r squared over the period squared, and we're dividing by r, which is the same as multiplying by 1 over r, and we can cancel out an r. And so there is our first expression for centripetal acceleration. That's that. So there's our first equation. So let's just take that and let's turn it into one that involves frequency. So the period is equal to 1 over frequency. So the period squared is equal to 1 squared over the frequency. And so we can take this expression for period squared in terms of frequency, and we can just substitute in our equation here. Okay. Good so far?
Yeah.
Oh, but I didn't square my pi. Pi. It's round anyway. And that's it. So 3 new equations Two new ideas. Acceleration is directed towards the center of the circle. Velocity in uniform circular motion is tangential to the circle. Centripetal acceleration is equal to the velocity squared divided by the radius. Or, potentially, it is 4 pi squared r divided by the period squared. Or, potentially, it is 4 pi squared f squared frequency squared times the radius. That's it.